Hello, physical science students, and welcome to our unit about electromagnetic waves. We're starting with this video that will be addressing what are electromagnetic waves. EM for electromagnetic. What are some properties of electromagnetic waves, and how do matter and electromagnetic waves interact? Here are some examples of electromagnetic radiation: gamma rays, infrared light, visible light, UV light, X-rays, radio waves, microwaves. So what do all those kinds of waves have in common? So let's review some of the things we've been learning. That waves are produced by something that vibrates, and they carry energy from one place to another. If we think about water waves or the sound waves that we've been talking about, the water waves are moving through water, sound waves are moving through air, and the waves travel because energy is transferred from particle to particle through the matter. Without matter to transfer the energy in water or sound, these waves cannot move. So what about when matter is not present? Well, that's where electromagnetic waves come in. They are produced by vibrating electric charges, not particles, but electric charges. They're composed of changing electric and magnetic fields. So instead of energy being transferred from particle to particle, energy is being transferred between electric and magnetic fields. So electromagnetic waves do not require matter to travel, because electric fields and magnetic fields can exist where matter is not present. So here's another review for us. Remember that electric charges are surrounded by electric fields, and that magnets are surrounded by magnetic fields. Also remember that when we have a moving electric charge, such as a current running through a wire, that wire is surrounded by a magnetic field. Remember also, a moving magnet is surrounded by an electric field. So a changing electric field creates a magnetic field, or a changing magnetic field also creates an electric field. And the interesting thing about magnetic fields and electric fields is that they exert force even when the charge or the magnet is not in contact with an object. So electric and magnetic fields can exist in a vacuum. A vacuum is just a volume of space that contains no matter or very little matter. So what does all this have to do with electromagnetic waves? Well, if we think about an electric charge, here's just a single electron. Let's say this is vibrating or having motion, such as in this current. That would, if we pick out one of the electrons from that current running through the wire, and we look at that individual electron, and as that vibrates, an electric field around it here, that changes. And that changing electric field generates a magnetic field. And a changing magnetic field generates the electric field, and back and forth and back and forth. This produces a wave. And that wave travels through space. That is the electromagnetic wave, due to the changing electric field and magnetic field interacting and continuing to propagate one another. So let's take a look at some properties of electromagnetic waves. The charge, if we pretend that this is the charge traveling, the direction of the charge, of the moving charge, the electric and magnetic fields travel outward from that. And the electric field and the magnetic field are always perpendicular to each other. They are at right angles or at 90 degrees to each other. So in this picture, the magnetic fields are being represented here, and the electric fields are being represented as going in this direction. So because they are perpendicular to each other, the electromagnetic wave is a transverse wave. Remember that our definition of a transverse wave is one in which the vibration is occurring at a right angle or at 90 degrees to the direction that the wave travels. So electromagnetic waves follow the wave speed equation. Velocity equals frequency times wavelength. And remember that this is a little bit of a review, but the wavelength and the frequency are inversely proportional. meaning when one gets larger, the other one gets smaller in value. So here we have our shorter wavelength, meaning there will be a higher frequency. And here when we have a longer wavelength, there will be a smaller frequency. Also, electromagnetic waves travel at the speed of light. Light is a type of electromagnetic wave, and in a vacuum, remember a vacuum is where we have little to no matter, the speed of light is 300 million meters per second, or you could say 300,000 kilometers per second. Travels really fast. Remember, the speed of light also is nature's speed limit. Nothing travels faster than the speed of light. It does matter, though, the material that the light is traveling through, or the electromagnetic wave. If the electromagnetic wave is traveling through anything except a vacuum, it will be just a little bit slower than this. So let's take a look at some of those values. So here are some speeds for electromagnetic waves in various materials. Notice that in a vacuum, we have 300 million meters per second, and you can see that in air, it's just slightly less than that. In water, there is definitely a reduction in speed, and in glass as well. So when light travels from air into water or from air into glass, we have a reduction in speed, and that's where we see refraction, remember from our last unit. Now there's another way that we can write these numbers. These are really big numbers with lots of zeros, and I'm going to show you how to write them in scientific notation. If we take a look at this number, we have 3, and we have a lot of zeros after it, and remember that we have an imaginary decimal point at the end if it's not otherwise specified. We can take this decimal point and we can move it 1, 2, 3, 4, 5, 6, 7, 8 places to the left. That gives us a 3 with a decimal point right after it. And we can write the zeros or not, but we have a 3 times 10 to the 8th. So that is how we can write this number in scientific notation. In essence, we are saying 3 times 10 to the 8th power. That means 10 times 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 10, 8 times. That will give us, if we take 3 and we multiply it by 8 tens, that gives us this number back again. So let's do one more. Again, we have our imaginary decimal point right there. We're going to move this 1, 2, 3, 4, 5, 6, 7, 8 places to the left. That gives us 2.99 times 10 to the 8th, written in scientific notation. Now, I'd like you to pause the video here and answer or solve these, write these in scientific notation. There's some little spaces, and then when you start the video up again, I'll give you the answers. Okay, here are the answers. Hopefully you got those right, and you can convert numbers into scientific notation. So let's look at the interactions between matter and electromagnetic waves. One thing to know, all matter contains charged particles that are always in motion. All matter does, and therefore all objects are emitting electromagnetic waves. The difference between these electromagnetic waves would be primarily due to their wavelength. We have very, very different wavelengths between electromagnetic waves, and when wavelengths are much shorter, they tend to be much higher in temperature. So warm objects, you know, would have a lot of energy. They tend to have longer wavelengths. So let's think about the sun emitting electromagnetic waves. And here we have an electromagnetic wave traveling through the vacuum of space from the sun to the earth until it hits an object and comes into contact with asphalt, let's say, for example. This asphalt contains charged particles and magnetic materials, and there is an interaction between this electromagnetic wave and this object. The electromagnetic wave will cause the electrons in this asphalt, in this matter, to vibrate and gain energy. That makes it hot. That energy carried by the electromagnetic wave is called radiant energy. Radiant energy makes things warm. It lets you see. So it may seem to you that the difference is very clear between a wave and a particle. We say that a wave is a disturbance that carries energy. We say that a particle is a little tiny piece of matter. However, the difference isn't always that clear. Sometimes light behaves like a particle. Light is an electromagnetic wave. And why would it behave like a particle? In 1905, Albert Einstein actually came up with this idea of a photon. Light travels in little packets called photons, which are bundles of energy that have no mass, and they simply behave like a particle. Light also behaves like a wave. We know in an example, if we were to have two slits and we were to shine light through them, we would get an interference pattern being formed. So light also acts as a wave. This is what we call the dual wave-particle nature of light. Light is both a particle and a wave. Well, this discovery that electromagnetic waves could behave like particles made scientists wonder if other particles might behave like waves, such as electrons. So here we're looking at an electron gun shooting electrons at this double slit. You know that if you were to stand here with a spray can of paint and spray paint over this, that behind it there would only be two slits produced, because that spray paint those are particles that are going through. They would produce simply two slits of spray paint on the other side. However, when this electron gun was shot at these slits, we see that an interference pattern was formed, similar to the one formed by light. So we know that electrons can also, even though they're particles, behave as waves. Scientists have since found that all particles can behave like waves. It doesn't mean that particles travel in wavy lines, it just means that particles can display wave behavior, like interference patterns that was once only associated with waves. If you're interested in advanced ideas, what are some ways scientists have measured the speed of light? Look at ways scientists have tried and failed at measuring the speed of light. How many minutes does it take an electromagnetic wave to travel from the sun to the earth? Here's the distance. Determine the speed of light using a microwave oven and the wave speed equation, following procedures on page 344 of your textbook. If you have other questions or ideas, please feel free to do those, and I look forward to seeing you in class.